also be late. Traffic unusually bad today. I've spent extra 30 minutes today in traffic, so will some other people. Some of the pictures from yesterday, all of them you can find on Blackboard if you're curious. Some pictures are really, really nice, but contradictory sometimes. Here what I see is a right triangle, vector addition, eventually a Pythagorean theorem, but in the middle of the whole thing is calculating the sum as the sum of two numbers. So this equation this equation assumes vectors which we can see here, but then treats vectors as numbers. And I've got pictures which are absolutely perfect. And here the picture, the triangle, and the calculation Pythagorean theorem consistent, but still many students draw already a correct picture, but then forget that vectors are not numbers and start calculating net field just by adding. See, this is a correct way to add vectors, but then something happens and you forgot that the vector is not a number and start adding numbers. And again, this is a very common situation, not one, not two. So just keep it in mind. Your calculation is supposed to be consistent with the picture you draw. Well, here the net arrow should be a little bit shorter. Here the net arrow should be opposite. Here we should add the square root. So little things like that makes difference. Again, absolutely correct picture, and then wrong calculation. Well, that's probably one of few situations when direction of magnetic field was drawn incorrectly. Right-hand rule. Now, a current is not a vector. Magnetic field of a current is a vector. So magnetic field is generated by electric current in a wire, but an arrow doesn't represent the wire. It's supposed to represent magnetic field. I'm not sure what those arrows are. Yeah. That's correct, because here we are looking at magnetic field generated by two currents, and extra elements usually might confuse people. Here, well, first, directions should be different, but also if you add those arrows, the net force is supposed to be consistent, and that's important, because if your picture looks like this, you just can't apply right triangle rules. You want to have a triangle. All right, so yeah, wrong direction for the net field. a picture like that, let's see if this works. A picture like that was a part of our reasoning when we needed to add 3 different vectors. We call them forces usually. It was about equilibrium, and the equation was first force plus second force plus third force is equal to 0. In that case, we get this triangle. However, if we are adding only 2 forces or magnetic fields, doesn't really matter, F1, let's say, plus F2, that's going to be this. Already? All right. So, okay. Please send me an email if you have any questions. But right now, I want to ask you what should happen in this experiment. I'm going to switch to the camera soon, but for now, this picture represents what's happening right here. We have a power supply or a battery, a switch, wires connected to the power supply, and these are conductive wires which actually can move left and right, up and down a little bit. An electric current should travel through, and as we know, a wire with a current basically is a model of a magnet, and as we know, magnets might repel each other or attract each other. So in this situation, when we turn on the current through both wires by closing the switch, well, these are only reasonable options to choose from. We can look at it and nothing might happen. Or we can look at the wires and they might move away from each other or toward each other. If they move away from each other, this phenomenon has a name, actually. Anyone, please tell me. When 2 objects want to escape each other, how do we call it? Repulsion, yeah, they would repel. But if 2 objects move toward each other, how do we call it? Attraction. So it's about repulsion and attraction. Exactly like with people, but simpler. All we need to know is right-hand rules. It's much more complicated and more rules when we talk about people. So you should pick your answer. Enter. Do I have it? If you want to talk to your neighbor, talk louder. First, oops, what's happening here? Oh, wrong. 12. No matter how loud you speak, I speak louder. So. What's happening? Lecture 12, summary. Okay. All right. So we have close to 50-50 distribution already out of 40. And well, now it's a good time to check your prediction if it's going to work, of course. Yeah. Theoretically, everything works as supposed to. There is a difference between physics and engineering based on physics. So, wires. And I want to run the current a long time, because that would most probably blow the fuse. High current, to make a force strong enough, I need a high current. So it's about 10-15 amps, which is relatively high current in regular setting. So look closely. What do? Repel. They repel each other. They don't like each other. But we can change that. How can we make them attract each other, by the way? Yeah, we have to change the direction of the current. But first we have to talk about why do they do that? We know everything about generating magnetic field, and also about a force acting from magnetic field on a wire. We just have to combine these two parts of physics we've learned. So that's the fact. And why? Why? Well, let's imagine that the switch is closed, right? So first, we have to recall the knowledge about electric current. How would it travel? The battery, well, makes fictional positive charges travel away from electrode with higher potential. So electric current would start here, and it would go through here, etc., and then it would go back into the low potential negative terminal. So here electric current travels to the right, to the left. Now we have to pick any wire and make it a source of electromagnetic, or in this situation just magnetic field, and that magnetic field should be acting on another wire, exerting a force. So which do you want to pick as a source? The top one or the bottom one? Thank you. So now, according to the right-hand rule, magnetic field generated by that wire, well, from my point of view, should be counterclockwise. So if I look at the screen, you look at the screen, the source wire generates magnetic field lines like this. So magnetic field goes out above this wire into the screen below this wire, including the location of the second wire. That's the magnetic field. Well, let's call them one. Magnetic field of the first wire. Now that magnetic field is acting on the second wire, exerting a force. And what rule do we use to relate the direction of a magnetic field, current, and force? Exactly. So magnetic field is into the screen. Now what should I do? I should turn my finger in the direction of the current. That gives the force. That is the force acting, well, we used to call them 1, 2, 2, 1, yeah, if we have two objects. So this is the force acting from on. And we can now switch the source and the test wire, but also we can now just apply the Newton's third law. If two objects interact, they must exert forces same in magnitude, but opposite in direction. So this is from 2 on 1. And that's what we saw. It's a good exercise in applying those rules in combination. So, can we make these wires attract? Yes, we just said we just need to change the direction of the current in one wire, in one. If we change the direction of the current in both wires, that's not going to change anything. So we have to change the direction of the current in one wire. So let's say I have to reconnect wires. This is physics. So the current should travel like this. Electric current should travel like this, and after that, like that. Now wire should be parallel. Attraction. See how it's simple in physics, from hate to love. Just switch the wire. And of course, the same reasoning tells us one wire source generates magnetic field, but now the force acting on another wire should change the direction to the opposite, so they attract each other. And there is interesting difference between charges, magnets, and wires. The nature plays a joke on us. We know like charges repel each other. Opposite charges attract each other. Like poles repel each other. Opposite poles attract each other. But if we look at currents, like currents attract. Opposite repel. Why? We don't know. Well, we don't care. We just have to know this rule. And a rule of thumb is this. You have two parallel currents. You look at the thumbs, they show you what's happening with the wires. Parallel currents attract each other. There is no rule for the opposite because we don't need it. If this rule doesn't work, that means they repel each other. Any questions? Of course, we have to talk about magnitude, and we can calculate the magnitude. If you want to, you can do it at home. Again, it's a combination of two equations. One wire generates magnetic field, B equals mu I over 2 pi r. Second wire feels the magnetic field and experiences force. Force equals IBL. We combine these equations. Turns out, when we have two wires, the magnitude of the force is equal to this. Current number 1 times current number 2. This, of course, is only a part when wires overlap. Yeah. That normally is the case. However, very often, we don't know the length. But very often, we don't need to know, but very often questions are about force per unit length. So for calculating or using, if we know it, force per unit length, we just do this. This is kind of similar to Coulomb's law, yeah, but instead of charges, we have electric currents, and the important difference is the distance is not squared, just the distance. It's because wires, not points, yeah, point like charges. One thing, many charges traveling in the same direction with constant speed, different thing. And you have a homework problem. Probably you have it solved already, but still, there's a homework problem when you don't know the mass of a wire, but you know the mass of 1 meter of that wire. That's what we call density. So for that situation, if you know that 1 meter of wire has a certain mass, and you know this M and that M, two different M's. So to calculate, well, that's mass of 1 meter. To calculate the mass of L meters, all you have to do is just multiply the density, the mass of 1 meter, and the length, if you need to. Just a review what density is. Now, if you don't have any questions, and you don't, we can start practicing. Here we have 5 wires. They're all perpendicular to the screen. That's why we don't see actual wires. We just see the electrode, yeah, like this, which looks at us. We also know that the wire in the middle has a current traveling away from you into the screen. How do we know? We know symbols. And the question is, how should we direct electric currents in other 4 wires in order to make the net force acting on the wire in the middle point like it points? So technically this is, again, trial and error problem, because what we can do is just check all options. How many options do we have? Out or in, out or in, out or in, out or in, for each. So 2 times 2 times 2 times 2. Many. 16, right? But naturally, if we want, this is a problem about vectors. This is a problem we have reviewed when I talked about your pictures. That's the goal. This is the goal. This is the goal. How can we make this work? Well, we have to have one arrow, force. One arrow which points like this. This arrow might come from the wire number 1 or the wire number 3. Doesn't matter, because another wire also should have this, should provide the same force, and otherwise they would cancel each other. But the forces due to wires 2 and 4, they should cancel each other. So it might be this plus this. And which is which? Well, those are all possible situations. So this could have been 1, 3, 2, 4, 3, 1, 2, 4, 1, 3, 4, 2, 3, 1, 4, 2. So if I want wire 1 to attract wire in the middle, how should I direct the current in wire 1? Attraction means they have to be parallel. Oops. So if I want wire 1 to attract it, it has to be parallel. So that's it for wire 1. But now, if this is my wire 1, my wire 3 is supposed to repel the wire in the middle. So it should have a current opposite to that. Now, wires 2 and 4, they should have forces either attracting or repelling simultaneously. So it should be in and in, or out and out. And that's it. So this is an exercise in what? Fingers and vectors, adding vectors. And of course, we can calculate, for example, we have to pick any configuration, let's say out, 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 okay? And calculate this force and the length of each side. So it's not the length of a wire, it's the length of this side of a square equals square root of 2. Why would people write square root of 2? So magnitude of each current equals 2 amps. 2, 2, 2, 2. And that's what we're actually calculating here. Net force per meter. Well, we just said it has to be equal to the sum of two forces, and they have to be equal to each other, same current, same distance, so it's basically 2 times 1 force. Which one? Doesn't matter. 2 times. So mu 2 pi I squared, because it's same current. The only tricky part is getting the distance. And we need to know that distance used in this equation is the distance between the wires. So we need to calculate this distance. Yeah, well, let's write it d first. D is D requires our ability to do triangles geometry. So actually I want to do big triangle, another D. So that's going to be a hypotenuse. 2d squared supposed to be equal to square root of 2 squared plus square root of 2 squared. So 4d supposed to be equal to 2 plus 2. Hence, d equals 1 meter. What a coincidence. So net force per meter will be equal to 2 times 4 pi 10 to the negative 7, 2 squared, 2 pi times 2. Eight times 10 to the negative 7, a Newton over a meter. Normally these type of problems are very straightforward, except they might require some geometry. Yes? I've converted this sentence into the equation. We just have to read it carefully. If it says per unit length, per meter, per something, that's what it is. Per means divided by, yes.
At the bottom of the equation, you wrote pi times 2 because
I wanted to ask you a question, so you did. Thank you. See? What day today? Thursday. Let's make Thursday a day of perfect ones. Now I'm going to pay attention to ones, not to twos. All right, a different configuration. 2 wires acting on the third one. The third one supposed to be placed at the origin. So let's just draw the third wire. And currents are different. Current 1 points out of the screen. Current 2 points out of the screen. Current 3 travels into the page, well, into the screen. Not each. That's and that came from, and current is 2 amps traveling into the page, 2 amps. So again, we need to calculate the net force per meter. Per meter. But now we just can't do it straightforwardly like we did it in the past, because configuration is different. Now forces, individual forces, not parallel to each other or anti-parallel, right? So we have to draw the direction of each force. Please draw the direction of each force. 2 arrows should show the direction of each force acting on the third wire. This current is out, this current is in. That current is out, this current is in. Right here, 2 forces should act in it. So please just draw 2 arrows. 1 arrow should represent the individual force number 1. What's the rule? That's the rule. Not this. This. Remember that. The rule. The party. The rule. So these 2 currents, 1 and 3, what do they do? Repel. Parallel currents attract. So if they anti-parallel, you can do it with your hands, anti-parallel. So just know parallel currents attract. So if they anti-parallel, they repel. So we should have a force down and a force left. Now we know what to do. We've done this before many times. F net is this plus this, which means this plus this. This blue arrow represents F net, and we know that F net is supposed to be equal to square root of F1 squared plus F2 squared. Well, what we're looking for is actually this. This might require slight algebra. We bring the length inside the square root. So to do that, we actually have to square it. Which actually makes our life easier, because now all we have to calculate is this. The first wire, 4 pi times 10 to the negative 7 times 30 times 2 divided by 2 times pi. What's the distance? 2. Yeah, I remember that. And now 4 pi times 10 to the negative 7 times 20 times 2, same current number 3, 2 pi 2 squared, square root. Now, of course, one way to calculate is quickly just take a calculator and do it. Another way, which I like, because that's how I was taught, is look at similarities, common factors. 4 pi negative 7, 2, 2 pi 2, 4 pi negative 7, 2 pi 2, these two. So we square it, and then we take square root of that. So what's left is exactly the same thing. Equals. Equals 4 pi negative 7, 2, 2 pi 2. What's left inside? 4 pi negative 7, 2, 2 pi 2. Inside we have left only 30 squared from this and 20 squared from that. So here a 7, that's a 7. So what's left here is 4 and 4 pi and phi this. And that's square root of 900, 9 and 4, 1300. Right? 9, which is actually 2, 10 negative 7, square root of 110, and what's left is square root of 13. 2 times 10 to the negative 6, square root of 13, 5 times 5, 25, 4 times 4, 16, 3.3, 2. Well, someone has to take calculator and calculate one number, square root of 13. 3.6. Thank you. So that's going to be 7.2 times 10 to the negative 6, a Newton over a meter. Yes? You wanted to ask a question? No? Okay. All right. I misread it. Any questions? Please. Again, this problem is more about geometry forces, vector addition, and right triangles than about physics, technically, again. Oops, where's all my calculation? Someone really hates me. What was it? 6? Question. So you will think about this question. I will prepare the demonstration, like an experiment. You make a prediction. As you know, in physics, all we do is for only two purposes. The reason physics exists, well, the reason science exists, to explain things or to predict things. So here you want to make a prediction. Here I'm going to have an aluminum bar moving through strong magnetic field, and to observe what should be happening inside it, I will be using a multimeter, very sensitive, which can measure potential difference. And the potential difference between two ends might be equal to 0, might be negative, might be positive. All I need is a strong magnet. And also strong back. Now, this is what I'm doing. Do you see anything? Of course not, it's not connected, I need wires. If I had any potential difference generated between these two ends, I can't feel it. No one can. So that's why we need an extra device to see that potential difference. So by now you should already make a copy of a picture. Pick your choice of the answer, because in 30 seconds you will not be able to see the question. Entangling the web of lies. Yes? That's velocity. It's moving to, in this situation, we move it to the right, and we have two ends, up and down. I could have tried to do it, well, that would be like this. Magnetic field points from outside of the magnet from north to south. That will be the magnetic field. So from your perspective, it goes into the screen, and this is the bar, so I can move it to the right, keep it vertically. It's just easier to me. Yeah. to move it up and down. Okay. So I wouldn't break these. Well, of course, the question is about, should we see anything? And the answer is yes, we should. It's about prediction. There is a difference between moving an aluminum bar and a plastic bat. What's the difference between these two? Aluminum is a conductor. A plastic bat is a dielectric insulator. Aluminum has a lot of free electrons which can be easily moved. With a plastic bat, no matter how strong, how fast I'm going to move it, nothing's going to change because electrons can't move. We have to apply a relatively strong mechanical action to make electrons move. Here, easily. So something should happen. And, well, let's see first. Well, I can't flip it over, so you just have to adjust your vision. Let's see. Well, you can just look straight at it. Did you see the motion? Yes. And now it's in opposite direction. Now, what's happening? Or I can move it. That's kind of harder. Like this. Or like this. Every time when I move it through magnetic field starts acting on electrons, which can easily move. So what's happening here, for example? Let's say I move it like this. So my hand makes electrons inside this bar travel to the right. And when a charge traveling through magnetic field, what starts happening? When a charge is traveling through magnetic field, there is a force. For the electrons, if you want to figure out the direction of that force, what do? We use left hand. We could have used right and then change the final direction, but it's just easier to use left hand. So an electron travels to the right, and the magnetic field points into the screen. So electrons should be collected, should be moved down, which means this end should experience deficiency of electrons, which makes it positive. So current travels through. We can see. So this is now basically a battery. It generates electric current. If I disconnect the wires, there will be no electric current. But still, the same magnetic field will be acting on the same electrons. Still, we will observe the same separation. So in this situation, still, this end will be positive, this end will be negative. So it still will be acting like a battery. And the property of battery is described by EMF. So when we have a conductor traveling through magnetic field, there is EMF induced in it. And of course, now being said that, we need to know how to calculate the magnitude of that EMF. Well, first of all, it has a name because of the motion of an object. We call it a motional EMF. It's generated due to the motion of a conductor in the magnetic field, motional EMF. Not emotional. Don't be emotional. Motional. Now, of course, here, well, okay, let's do the picture. An electron, the velocity, left-hand force. So we should have electrons collecting here, and here we should have some region with deficiency of electrons, and it starts acting like a battery. That motion of electrons from top to down can't happen forever. Eventually, the new equilibrium has to be reached, like always in a conductor due to internal resistance. When? Well, when eventually the force exerted by magnetic field, that force which makes them travel, will be cancelled out, compensated by a force of electric field generated inside, because we have minus and plus. It's like a capacitor also. So electric field always points from plus to minus, from high to low. And that electric field also will exert a force. And eventually they become balanced out. So eventually the force due to electric field induced by the separation in the electron distribution, induced by the magnetic field, yeah, but still getting cancelled by that force which induces the motion of the electrons. Turns out in this situation, it could have been even protons or ions, the charge getting cancelled. So it's actually a property of the magnetic field, electric field, and the length of that conductor. So this is the amount of EMF induced inside a simple conductor, simple, a bar, traveling in a simple magnetic field, uniform, when everything is perpendicular to everything. What everything? Well, one direction represented by the bar, second direction is represented by the velocity, third direction is represented by a magnetic field. So this is the simplest case, easiest one, when everything is perpendicular to everything. What do we do if that's not the case? We just use components which are perpendicular. You can imagine magnetic field and a bar and velocity. Relative to this bar, any vector always has two components. If this is a magnetic field, it has component parallel to the bar and perpendicular. Well, maybe it doesn't have. In that case, that would be zero. If this is the velocity, again, it has perpendicular and parallel. If it doesn't have perpendicular, again, that would be zero. So both variables, magnetic field and velocity, should have components perpendicular to bar. In that case, we get EMF induced in it. So that's a conclusion. A conductor, simple bar, in a simple case when everything is perpendicular to everything, starts acting like a battery. Question. It's not a bar anymore. It's a circuit like in my experiment. A moving bar, wires, instead of a multimeter, here I just use a resistor, maybe a bulb, and I move the same bar in the same direction with the same magnetic field. The question is, what's supposed to be the direction of electric current through the resistor? And this is where we combine things about magnetic field and things about circuits. What do you say? What do you think? Smart. There is electric current in the circuit. If I ask, what is the direction of electric current in the circuit, you should say counterclockwise. But if the question is, what is a direction of electric current through the resistor, you should say through the resistor. How do we match counterclockwise and up?
Oh, no, I mean...
We just said that a moving bar starts acting like a battery, and we know in this particular experiment, it will act like a battery with a plus and a minus, like this. Plus, minus, so electric current should start traveling outside of the battery like this. That's what we call counterclockwise current in the circuit, or down to the battery, right? So again, this is just a kind of review of a terminology we use. But sometimes if we read the problem about a current through something, we need to know the terminology. Problem. A loop is made of a 2-meter-long rod, conductive rails of wires, a bulb, and we know the total resistance. And there's magnetic field, and we start moving the rod by applying the force. Our hand moves the rod. And many different questions. But basically, find everything. Yeah, that's what we say. So, first, just redraw the picture. A bulb doesn't really have to be a bulb, could be any resistor, of course. And right here, right now, we have a rod, magnetic field, B points into the screen. And we move the rod to the right. Well, the initial velocity, let's imagine what's really happening. The initial velocity is 0, we grab it, and we start moving it, and we keep moving it by applying the same force. And when the rod is at rest, there is no velocity, there is no EMF, there is no current. But as long as we start moving the rod, we induce EMF. We know that this circuit is equivalent to this circuit R. But this EMF depends on the velocity. I can't immediately start move this rod at certain speed. I have to go from 0 to certain speed. So initially, over certain time, maybe second, maybe seconds, maybe fraction of a second, but initially velocity changes and EMF changes. But electric current in the circuit, this is a simple circuit. The Ohm's law tells us how to calculate electric current. If EMF changes, electric current changes. So it kind of makes things more complicated. But there's one more thing we didn't mention yet. So we know there's supposed to be electric current traveling in a circuit counterclockwise. We know that means there's electric current traveling down through the bulb, but it also automatically means, what do you think it also means? Because? So why do you skip a step? You have to go step by step. First, we have to say, there is a current through the bar. There is electric current, thank you, exactly. There is electric current through the bar. It travels all the way, you know. But if there is electric current, and magnetic field acting on it, there must be a force acting on it. What is the direction of that force? Well, current, field, force. So there's magnetic force, which is opposing the applied force. So we have two forces here, applied force, due to a hand, but there is also magnetic force. How do we calculate magnetic force? Magnetic force, ILB. So if velocity changes, EMF changes. If EMF changes, current changes. If current changes, magnetic force changes. From what to what? From zero, when nothing was moving, to what? Well, if it grows with velocity, eventually it should reach the magnitude of the force we are applying to the rod. Eventually it should happen. So, for the magnitude of the force, eventually we should get to the applied force. What starts happening when it's happening? We have one force directed to the right. We have another force which has exactly the same magnitude but directed to the left. No, they can't.
Constant velocity.
It reaches constant velocity. That means net force equals zero. That means acceleration equals zero. But it doesn't mean velocity equals zero. That means velocity now, from this point forward, remains constant. So if we want to sketch a graph for velocity as a function of time, it also like this, from zero to a certain value. People call it terminal velocity. In many phenomena like that, when velocity changes but eventually reaches some fixed value, we call it terminal velocity. And that's what I think we're looking for. Yeah. So that's one of the questions. We need to calculate everything. So let's calculate everything we can, assuming that time is much more greater than zero, assuming velocity remains now constant. Now we just have to put together all these equations. What do we know? 2 amps. Current, magnetic field, the resistance, the length. All right, that's it. Current, field, and length gives that final magnitude of magnetic force. Which automatically tells that the force applied is supposed to be equal to that maximum value. Maximum, let's say, maximum. Current and resistance tell us EMF, and the EMF, length, and magnetic field tell us that terminal velocity. Do you see it? That's what we know. We know all 3 variables here, that's a number. We know 2 variables here, that's a number. We know 1, 2, 3 variables here, that's a number. Done. And I think I have the answers, yes. So that's the logic. Where? Well, at least the screen is not blinking. Everything I wrote just gone. That's annoying. All right. One problem has been solved that raised a different problem. Question. I think that's my last demonstration for today. So what we have here, a battery or a power supply. And what's the difference between this question and the question before? We'll see. Before, we didn't have any batteries in the circuit. It was a bulb, a rod, magnetic field. So this is a new situation. Pay attention to a new situation. Well, now we have a battery. And we need magnetic field. I didn't check this. I don't really know if it's red, it's blue, so let's, if that would have been red, that would be north, south, north magnetic field would point like this. Okay, let's assume it's red. Now I need electrodes. And in the air, they quickly get oxidized. Now I need a rod which can move. Now I need to connect the wires to a power supply. So, what should happen? Let's say we close the switch. So, electric current should start traveling like this. How do we know? We took and examined that. So, electric current through the bar should travel up, and if magnetic field here points into the screen, if we apply the right hand rule, the force should act to the left. Now, if my magnet, all right. Yep. See how I move it. That's what magicians do. They make you look over there and then take your wallet. But that's physics. If we know the properties of this system, the prediction, well, of course, if we switch direction, magnetic field or current, it will travel in opposite direction. And if the magnetic field is very strong, it actually can travel very, very fast eventually. And that's what people call electromagnetic gun. It can shoot bullets. Some people thought of using this in outer space as a weapon. There's no oxygen, so you can't blow things up outside, but electromagnetic field is everywhere. So you can weaponize it if you want to. Well, that's a different type of problem, so we need to solve this problem again. And we just need values. So battery, length, magnetic field. But the reasoning is not exactly the same, but very similar to the reasoning we've used for the previous problem. What's happening? Again, it is all about what's happening. That's what physics is about. It is not never ever about what we're looking for. So a picture, which as we know very well worth 1,000 words. A bar, minus, plus, and magnetic field, and electric current. Well, again, before the switch was closed, there was no electric current, and nothing happens instantaneously in the universe, nothing. So electric current should start from zero when we closed the switch, but should increase, and eventually should reach some maximum value, terminal value, maximum value. Now, as long as we close the switch, we get electric current in magnetic field, so we should have a force acting on it. And in my example, that force should point to the left, well, wherever. Doesn't really matter. We can assume those rails are really long, so it can travel long period of time. So force, yes, that's the magnetic force. If current changes, magnetic force changes, and eventually also should reach some maximum value. Which one? Well, now we know that as soon as conductive bar starts traveling in magnetic field, it becomes a battery. So this very bar now can be replaced with the battery, current-wise. Well, and for that battery, the magnitude of EMF should be equal to Wibble. No. Blv. Question is, where is the plus, where is the minus for that battery? Okay, this is supposed to be longer, because this battery is given 90 volts, plus minus. Well, now we can repeat the reasoning we used before. It is up to us if we want to repeat literally the reasoning about the electrons, or we can imagine fictional positive charges, because according to a definition, the direction of electric current is equal to direction of the fictional positive charges. So if I had any positive charge here, that would be moved with the rod to the right, and magnetic field acting on that positive charge would make it move down. So this end would become positive, that end would become negative. So the second battery, fictional battery, motional battery, would be connected in order to cancel the EMF of external battery. So what's happening? When the rod starts moving, velocity increases. This EMF, motional EMF, increases, but not forever. Eventually it reaches 90. It should happen eventually. And after that, what? After that, there would be no total electric field in the current. There would be no current at all. So Well, this is what motional external, when time is greater than 0, this is the condition which tells us what to do. The motional EMF eventually reaches the same value. Which is 90. And now we need to remember the difference between the net force and individual force, magnetic force. So that magnetic force, which could have been, well, which is actually initially makes it move. Where is it? Where is it? What we're looking for? Okay, terminal speed, terminal speed. So magnetic force will be cancelled by another magnetic force eventually from the opposite current, no current, eventually no magnetic force. But the terminal velocity reached by, I don't know what I like more, Wibble. By this equation, EMF equals Wibble, V equals EMF over BL, and in this situation that's 90 over 0.5 times 2. 0.5 times 2 is 1, so that gives a simple calculation for that terminal velocity. In reality, it all happens very, very quickly. The reaching terminal velocity, reaching equilibrium, happens usually fractions of a second. We can't even measure it. If you drop something from very, very high altitude and it travels through the atmosphere, eventually we know it reaches terminal velocity. That's how parachute works. But it takes time to travel to reach the terminal velocity. With electric phenomena, it all happens very quickly. By the way, I didn't talk about that before, but it's a good place to talk about. When we turn on the switch, light goes on immediately. But if you remember, we've mentioned that fact, you can Google it. Electrons actually travel very, very slowly, millimeters per second. So we turn on the switch, the bulb is on, but those electrons actually might not even have time to get to the bulb from the switch. So what's happening? Well, when we turn on the switch, electric field, which travels with the speed of light actually, immediately starts acting on all electrons in the circuit. So immediately all electrons start traveling with a terminal velocity, including those which are in the filament of the bulb. So here when we start, turn on the switch, immediately, almost immediately, the equilibrium again is reached and it starts traveling with a constant velocity. So we know now very well what's happening to a rod traveling through a magnetic field. Next question is, what should be happening to a loop? How a loop looks like? Well, normally we imagine a circular loop, but could have been rectangular, triangular, any loop. The word loop means continuous, that's it. And if it's a plastic or paper loop, conducting, insulating loop, no matter what we try to do, we cannot induce electric current in it. But if we have a conductive loop, something should happen inside it when we move it through the magnetic field. What should happen? Well, first of all, we know our expectation is clear. We should start observing some EMF, and to see that EMF, we need to measure electric current, but electric current has to be strong enough, so we can't use just one loop. We should use many. all we need to do is just connect a loop, meaning many, to a device which measures electric current and which is sensitive enough. Oops. Doesn't really matter, just for the demonstration. All right. I don't want anything happening here affecting what's happening there. So now we need a magnet, standard bar magnet, and we can just place it inside it. It's inside. Now we can see nothing. All right, I'm going to try again. If I take it out, would it make any difference? Again, nothing. That's exactly what happened to a physicist whose name now no one remembers. He was looking for connection between magnetic field, electric current, and he was afraid that magnet would affect the measuring device he used, so he kept it in different rooms. So he couldn't actually see what was happening when he was moving magnet in or out. That's sad. But Michael Faraday, he actually saw it. He observed that when a magnetic field inside the coil changes due to whatever reason, it doesn't have to magnet moving, it could have been coil moving or relative motion. For whatever reason, if magnetic field starts changing, it excites electrons, makes them move, we observe electric current. And the law which describes this phenomenon naturally has a name, Faraday's law, not the name of that person who no one remembers. Well, now we got to go through some theory. I got 10 minutes for that. First, we got to be able to imagine what's happening inside. Inside, we cannot see inside of coils or magnets. We have to use our imagination. Two different situations. Case number one, a uniform magnetic field. Same direction, same magnitude. So like this. Okay. The loop travels. So if we use our imagination, we extend those lines, those magnetic field lines, and no matter how fast or slow it travels, no matter where it is, the number of magnetic field lines through the loop doesn't change. 5, 5, 5. Now, it still is a conductor. Still, every electron should experience a force acting from magnetic field. What type of force? We know Lorenz's force. For example, let's take an electron here. It travels down, that's velocity, and magnetic field at the location of the electron points like this. So there has to be some force acting from that magnetic field on this electron. What is the direction of the force? Well, we need a perpendicular component of velocity. This is V perpendicular. Now we can apply the left-hand rule because it's an electron. V perpendicular. It's very hard. Okay. Into the screen. So the force acting on this single electron should point like this into the screen. So in my example, let's say it's here. I move it like this, that's magnetic field. Force should point like that. But on the opposite side, there is exactly the same electron with exactly the same magnetic field, experiences exactly the same force, but in opposite direction. Well, the same direction relative to screen, but opposite direction relative to that electron. They want to travel opposite inside this loop. Opposite means opposite. They should travel with same speeds, opposite velocities. Nothing should happen. That was that picture. There is difference if magnetic field is not uniform anymore. It's not like this. It's like this. Stronger magnetic field, more magnetic field lines per square meter. Weaker magnetic field, less magnetic field lines per square meter. So if we move a loop through non-uniform magnetic field, now those two electrons will experience different forces. This one shouldn't experience practically any force if that's velocity, that's magnetic field, 180 degrees. This one should experience strong force, electron, velocity, magnetic field. So now those electrons should start traveling inside that loop, which means we should observe electric current. That's it. And if we should observe electric current, that means there's supposed to be EMF induced. And if EMF is induced, that means there's supposed to be electric field induced inside it. But that electric field is not static. We cannot explain the presence of that electric field by just static charges. That's a completely different type of electric field, which is generated by, well, change which is happening inside this loop. It has no name, electric field, but not static, induced. And now, well, so this is a summary. Uniform magnetic field, no electric current induced. Non-uniform magnetic field, induced electric current not equal to 0. So if a moving rod is acting like a battery, a loop moving through magnetic field starts acting like a circuit with a battery. And of course, we will talk about the direction, how we can figure out what is the direction of that electric current. But first, since it's important what is happening to the number of magnetic field lines inside, we need the physical variable which describes the number of magnetic field lines inside the loop. This number. That number might remain constant. That number might change, but that number exists. So what do we do in physics? We give a name, a definition, a unit. This is a definition. The number of magnetic field lines inside the loop we call the magnetic flux. The flux usually a word representing something flowing through something. So magnetic flux. This is an efficient definition. That's a Greek letter phi. Magnetic flux. That's a definition. That's how in physics we count the number of magnetic field lines. It should be equal to magnetic field strength, well, technically average, if it changes, but we only, well, that doesn't matter. Magnetic field strength, or average, inside the loop, it should be equal to, well, multiplied by the area of the loop, and multiplied by cosine of the angle. This is where people get confused sometimes, because when we have a surface, when we have a loop, to describe the orientation of a loop, we use a special vector which we call, how do we call it? There is a special vector which we use to describe any orientation of any surface, or including a loop. That vector always perpendicular to it. So how do we call it? Perpendicular in physics. There's a word for that in physics. Normal, starting from normal force. It's a normal. So remember, it's not normal to forget the normal. We also call it area vector because we make it equal to the area. So this is the normal area vector, and this is the magnetic field, and theta is the angle between magnetic field and the normal. So you see, in this example, I really need the third hand. Normal. So that's magnetic field. So if theta is 0, we have maximum flux. If we start changing theta, rotating, the flux changes eventually to 0. No lines get through the loop anymore. That's basically what this is for, to measure how much magnetic field travels through the loop. 0, maximum amount, and something in between. Maximum, 0, and something in between. And if we multiply the units, Tesla, meters squared, no unit, that unit has a name. You can choose the way you pronounce it. People call it Weber, Weber, Wober. Whatever. Question. The last question for today. What do you think? You choose your answer, you enter it in a WebAssign, and then immediately you can rise, do your thing, and walk out. Unless you want to know the answer, of course. In that case, you should wait a little bit longer, like a minute. What did you say?
Never.
Never? Never? It's about angles. The angle, any angle can be measured between 0 and what's the maximum? Normal maximum, 360. Yeah, so cosine of 180 equal to,
But that would be 0, right?
okay, cosine of 120 equal to,
No, I mean like theoretically that would be 0 flux because there are no.
no? See? Cosine of 120 degrees is equal to negative square root of 3 over 2. Just plug in a number, cosine. Any angle between 0, any angle between 0 and 90 gives you positive cosine, but from 90 to 180 gives you negative cosine. So whatever number you get here, so it can be anything. It can be 0, it can be negative, it can be positive. It can be anything depending on the angle. Good morning.
I can't speak.
All right.